Before we look at electrode potentials and electrochemical cells, it's important to review what we already know about redox. So we know that redox is the process of electron transfer. So the redox is sort of shortening of reduction and oxidation. And using the mnemonic oil rig, we can remember that oxidation is loss, reduction is gain, but we must be very precise at A level and say that oxidation is loss of electrons, not just loss, and that reduction is gain of electrons. And then it's asking us to do an example of a reaction between bromine water with a solution of potassium iodide. So it'd be worth pausing the video and then having a go at writing down this reaction between bromine water and potassium iodide. So if you've done that, you would have seen that we've got bromine, Br2. The fact that it says water means it's AQ. Solution is another way of saying AQ, potassium iodide, and we're making potassium bromide and iodine. And I already started to balance this as I went along, but you would probably put these numbers in afterwards. You need to put 2 in front of each of these. Now, if we're going to decide who was oxidized and who was reduced using transfer of electrons, we'll probably need to convert this into an ionic equation. So again, have a go at converting this to an ionic equation. You can, if you feel confident, you might be able to do that in one step. If not, you might need to take a couple of steps to get there. But Br2 is not ionic, it's a covalent compound. So despite being AQ, that's irrelevant because it's covalent. Potassium iodide contains a metal and is therefore ionic, so we're going to split that up into potassium ions and iodide ions. When we look over at the other side, we're going to also have potassium iodide ions and this time bromide ions. So the potassium ions are going to cancel. Now, if I were to put them in, I'll just put them in for now. I would have 2K plus and 2I minus. And over here, I would have 2K plus and 2Br minus. And then iodine is a covalent compound, and so that will not split into ions because it's not ionic. What we can see is that we can get rid of the potassium ions on both sides, and we have the ionic equation. So this is the ionic equation rather than the full chemical equation. It then helps us, if we look at that ionic equation, to split this up into what was happening to bromine. So bromine is going from Br2 to Br minus. So if we have a look at that first. So if bromine is going from Br2 to bromide ions, in order to balance that, we would need to add 2 electrons to this side. And so this is reduction. Because bromine gains electrons. If we then want to have a look at what happens to the iodide ions, we can see that the iodide ions, 2I minus, are becoming I2. And to balance that, we put the electrons on the right, and so that is loss of electrons or oxidation. So iodide ions, not iodine this time, lose electrons. So it was a lot of effort to find out who got oxidized and who got reduced. So we remember from our previous study that if we were to use oxidation states, it's a little bit quicker, a little bit easier to decide who got oxidized and who got reduced, but we can't rely on that mnemonic to help us, so we can't rely on oil rig. We have to remember that oxidation is when the number increases and reduction is when it decreases. So I like to say, if the number is reduced, the element is reduced. So reduction is reducing the number. I'm going to write another equation. Again, pause the video, have a go at writing the equation between copper sulfate. So I'll start you off with the formulas. Copper sulfate solution and zinc metal. What would you make out of those two? So hopefully you've realised you're going to make zinc sulfate. Now zinc can only be a 2+ ion, so that's the formula of zinc sulfate there, and copper metal. So if we were to put oxidation states on this, we would see that at the start the copper is +2, copper 2, and at the end it's an element, so it's 0. And the zinc is starting off as an element 0 and ending up as +2. So we can see that zinc's number's increasing, so zinc is oxidized because its oxidation state increases. And that copper is reduced, its oxidation state decreases. So we've got some questions here for you to have a go at. We want to state which element, so when we're doing this, use the name rather than the symbol, because sometimes when we're using the symbols, we'd have to pay attention to charges. We're going to use the name of the element. So we're going to write the word out rather than using a formula. So state the element which is oxidized and which is reduced in each of these equations. So we're just going to have a look here. We've got an element here and an element here. So these are both 0. So these are the two things that are going to change, because unless they're an element on both sides, then they wouldn't be in the equation. They can't stay as 0. So on the other side, sodium in a compound is +1. So sodium's number's increased, sodium is oxidized. And then we can see in water that each hydrogen is +1, oxygen is -2. So hydrogen's number has decreased. Here we can see we've got chlorine as an element. Over here we've got chlorine in a few places. Here chlorine is the ion, so it's -1. So chlorine's number's gone down, chlorine is reduced. But we've also got another chlorine here. And in this compound, if the whole thing equals -1, sorry, this compound ion, and oxygen is -2, then the chlorine must be +1. Remember that chlorine is -1 except when combined with oxygen or fluorine, which are more electronegative, and therefore they are the negative, and so chlorine has to take on a positive oxidation state. So it's actually chlorine that is both oxidized and reduced. If you remember from group 7, this is called disproportionation, where the same element is both oxidized and reduced. And then on our last one here, one of these is fairly easy to see. We've got a +4 to +3 on the cerium, and so that has been reduced, the number's gone down. So what's gone up? And if we have a look, the hydrogen's +1 in water and +1 at the end, so it's not the hydrogen. In this sulfate ion here, we've got 3 oxygens at -2, and we're trying to equal -2 for the charge. So this sulfur's +4, whereas on this side, because there's extra oxygen, this is +6, and so sulfur has been oxidized. So our last little bit of revision is, what do we mean by oxidizing and reducing agent? When we're doing these, we're going to use the formulae from the balanced equation when we're referring to oxidizing and reducing agents, rather than the element that undergoes oxidation or reduction. So an oxidizing agent causes loss by accepting electrons, and a reducing agent is the cause of gain, and so it has to give electrons. So go through this example. We can see that in this first species, Mn is +7. You should have a go at working these out. and at the end it's +2. To go from +7 to +2, Mn has to accept 5 electrons. Let's go 5 steps down the ladder. So it has to accept electrons, which makes it an oxidizing agent, but we're going to write the full formula of that contains the element undergoing reduction is the oxidizing agent. So the full formula is MnO4 minus. Now we need to find what number is changing in the other direction. And we can see that the hydrogens are going to be +1 on both sides. In this ethane dioate ion, 4 oxygens each at -2, got to equal -2, so we need +6, but split up between 2 carbons, so they're each +3, whereas here the carbons are +4. And so the carbon is being oxidized, the element carbon is being oxidized, but the ethane dioate ions, therefore, must be donating an electron. So each one is donating an electron to go up the ladder from 3 to 4. So the C2O42 minus ethane dioate ions are the reducing agent. So pause the video and have a go at these 3 questions, identifying the oxidizing and reducing agent, and then come back and see if you got them right. So we should have got vanadium is +5 here, but +4 over here, which means the VO2 plus is the oxidizing agent, and that sulfur is +4 here and +6 over here, which means that SO2 is the reducing agent. Copper is 0 and then +2. Each nitrate ion is -1, so the copper is +2, which means that copper, because that's the full formula, is the reducing agent. The nitrogen in nitric acid is +5, and the nitrogen in nitrogen monoxide is +2. And so the nitric acid is the oxidizing agent. The nitric acid caused copper to be oxidized. Fe is +2, and it's gone to +3. So Fe2 plus, so iron is being oxidized, iron 2 plus is the reducing agent. The chromium in dichromate is +6, and over here it's a chromium 3 ion. So dichromate is the oxidizing agent.